Alright, so I want to get rid of the vagueness that I ended the other video with. If we're rotating with the y-axis, the solid of revolution is such this. And if we're rotating with x-axis, it's this. And this one makes sense because y is a function of x. Take the derivative with respect to x. But this one should also make sense. X is a function of y because you have to define x the other way if you're going to work with it over this axis. Wow, that's not right at all. Either. No, that's just check my drawing because that was wow. All right, there we go. So if we have to define it in terms of the y-axis and then integrate with the y-axis changes. So that was something I didn't state very well. But if you look, these are pretty much identical. But also notice the bound changes. I just labeled the bounds just in case, because you have to talk about the bounds here as A to B. So it turns out that if you flipped it onto the x-axis like this, it would still be A to B, this equation. Alright, so that's the idea here. And this is all part of what we call the disk method. Or depending on where you are, we also spell disk like this. It's both ways. Don't criticize me for this. Disk method. That's an OD. Alright. But there's one other way we could integrate. So imagine this. Imagine we have this curve. Let's say like e to the x. Alright. You have this curve e to the x, and we're only taking it from 0 to, I don't know, 2 or something like that. Imagine this though. What if we had this shell? What if we had this like piece that goes around it? And we found the area of the outside piece and kind of multiplied it times that tiny change in x. And then what if we add it all up? I have a feeling that if we did that enough times, we'd get all sorts of little cross sections. And this is so here we're kind of constructing a bunch of, what are they called, cylinders, and considering what the radius does and what happens to each spot as it goes around. So we have a bunch of cylinders here. We have an inner cylinder, we have an outer cylinder, we have inner cylinders, so the cylinders in between those cylinders, and it all goes together to create this one image of the volume that we wanted all along. Right? Looks a little sloppy, but you should be getting the idea now. So all we need to do is write up some way to find this. If we go dx in, if we have a height, what is the height here? That is our function. And then we have let's unravel this for a second. That would be a rectangle. And the top would be the circumference, so it's the radius. 2 pi times the radius, and the height we are set as f of x, and then we give it some depth of d of x. So if we multiply all of these guys and add them all up as we move, we should be able to find the volume. And even better, with only caring about the x-axis, so we don't have to do any of this converting from y-x to x to y. We can just work straight from this. So how do we go about it? Well, before we continue, what is r in this case? Remember that the center is 0. R, depending on what shell you're on, is just the x value to get to that shell. So if you take a point here on the x-axis, it's going to be your x comma f of x point. And so your height here is f of x. as you can see there, then our length, our radius, is x. So it's no longer r here, it is x, 2 pi x. And then this area right here is f of x times 2 pi x. So 2 pi x times f of x. And then we want to give it some depth, so multiply it times all change in depth, that dx. And now we add everyone from sum A to sum B, as always. And ta-da! This is called the shell method. Oops. Shell method. Because rather than making all these discs, all these little, we also call it washer if we cut out the middle, because they look like washers, like you put on gears and stuff like that. I mean, screws. So this is called the shell method, because you're kind of putting a shell around each piece. And so let's see how this works in action. Let's try this e to the x problem on the next page. All right. So switching pages here. Wow. All right, here we go. So let's try that e to the x problem using this idea called the shell method. And let's rewrite the formula, 2 pi x, because that's the circumference, and then the height, which is our f of x, and then the depth, dx, and we're going from A to B. Now, a function we're going to work with here is e to the x from 0, when this distance is 1, to 2, when this distance is e squared. That's 2, that's 1. I mean 0. All right? And we're going to rotate this around the y-axis, creating this awesome little dome kind of shape. That's just a cross-section of it, but you can imagine it rotated here. And we'll get this awesome little dome. So maybe you can make a bowl. Calculate the volume of a bowl with this method. I don't know. The world is your oyster. That's what. The world is your shell method. All right, whatever. Let's just get into this. So our curve is f of x, is e to the x, I mean. We have 2 pi, let's figure that out, and we have an x here. And we have it from 0 to 2. 0 to 2. So this shell method tells us, oh, don't forget dx. So we just have to calculate the integral and plug in our bounds. So what is the integral of x e to the x dx? Well, I'm thinking, do you remember that little thing we call integration by parts? Yeah, we're going to use that. And here, I'm not going to do much of a reminder, so you may want to review that video if you forgot this. All right, but here's what we do. We say that, let's just write what the rule says. It says that if you have a u dv that's equal to u times v, it's a u times v minus the integral of v du. You just pattern match with these variables. A uv, a u, a v. You might be able to remember it by like uv light. I don't know. You can decide these things. So let's set a u equal to x, because I want that x to go away when we put it in this portion right here. That du is just 1, right? 1 dx. And so that just goes away. Now what else can we do? We can say that, well, if this is x, then our dv has to be e to the x. And this is nice because the integral, we have to take the integral if we're going backwards, is just, and that dx is just because we have a dx right here, is just e to the x. So that's nice. Let's plug in. So u times v is x e to the x. Then we subtract the integral of v, that is 1 dx. I mean, that is e to the x. And then du, which is just 1 dx, or dx by itself. All right, and what is the integral of e to the x? That is just e to the x. So we get x the integral of x e to the x is x e to the x minus e to the x plus a constant, because that was the indefinite integral we just took. And before we continue, I'm going to factor that e to the x, because that's going to make our day happier. That's x times e to the x, and this is 1, negative 1, times e to the x. And then we still have that plus c. So let's plug that in now. So we have 2 pi, and now we know that the derivative is e to the x, and we get rid of the plus c because we know that will cancel out if we subtract it. So x minus 1, and we plug in 0 and 2. So let's get going. So 2 pi, that's still there. E to the 2 is e squared, and then 2 minus 1 is just 1. All right, that's good. Yeah, 2 minus 1 is that. So I just want to make sure I don't make any mistakes. And now we subtract the other results. So plug in 0 here. E to 0 is 1, and then 0 minus 1 is negative 1. So what does this become? That becomes 2 pi, and that becomes e squared times 1 is e squared. And this becomes 1 times negative 1 times negative 1, which is positive 1. So e squared plus 1 times 2 pi, let's factor out that 2 pi. It becomes 2 pi times e squared. That's a lot of constants in one thing, and 2 pi times 1. That is our exact volume of this interesting dome shape. Now let's say you're thinking, oh, I want the dome, but all we got was that shell that the dome is on top of. Oh, no, don't worry. I have an idea. And this is purely just in the moment, because this distance here is 2, right? What is this whole cylinder volume? Well, that's easy. That's just the bottom. That's pi r squared. So 2 squared is 4, so 4 pi is the bottom, and then we multiply that times the height. The height is e squared. So 4 pi e squared is the total height, is the total volume here. So if that's the total volume, and this is that piece that we took off, then what is this, a dome in the middle that we want to calculate? Well, easy. 4 pi e squared minus all this stuff. So 2 pi e squared minus, we have to subtract that 2 pi. And that's the volume here. And let's do some simplification. That's just the volume of that dome that encircles e to the x. That's 4 pi e squared, and that's just 2 pi e squared. So subtracting 2 from 4 leaves 2 pi e squared minus 2 pi. And we're done. Not much thought there. All right, so that is the idea of the shell method. And in the next video, we will be doing a lot. And so I'm going to push everything into that video. Thanks for watching so far.